Okay, so that's okay.
Yes. Yeah.
Yeah, so I just started by defining when the most basic notion of a geodesic metric space, or metric space is geodesics. If between every 2 points there is a geodesic, meaning an isometric embedding between the interval of the length between these 2 points to these points, right? So sometimes. And then in general, by geodesic, I will mean either this map connecting to points or the image. So I will confuse the map and the image. So a geodesic is a or geodesic array, respectively. Geodesic array. And I can look at everything. Or an interval. Respectively, we talk about geodesic arrays. Respectively. Positive parts. But as I said, geodesic can be both the map or the image of the map. Yeah, so now we'll start with the main definition of this store. So hyperbolic metric space. So metric space M is delta hyperbolic. Yeah, so we assume that is energy geodesic. For every key point, X, Y, and Z, if you look at the geodesic triangle between these 3 points, so you take 3 points and you connect them by geodesics and you construct a triangle. The triangle is in some sense fitting. So let me explain what this means. So for every geodesics delta X, Y, so Y is some geodesic connecting X and Y, delta Y, Z, and delta X, Z.
A moment, I certainly cannot.
It's not looking. It's working good.
Yes, I tried before the lecture and it didn't work. And it's slow. Maybe some button? Yes. Okay. To start camera. Yes. Okay. All right. Thank you. Because I didn't know it's a sensor.
Yeah, so metric space is delta hyperbolic. So delta is something which is greater or equal than 0. If for every 3 points from M and for every geodesics connecting these 3 points, each one of them is in delta neighborhood of the other 2. So each of the geodesics, each of them, let's say, delta neighborhood. So what that means, if you take, for example, any point from, so now I identify each of the six with the images. So if you take any point, like the line of this geodesic, then there exists some W line in the union of the remaining two. So you know that you know that such that this thing them is at most delta. But W and W is less than delta. So I guess it's easier to demonstrate on a picture. So let me draw a picture. So I take 3 points. And you can visualize the triangle, it looks like something like this. Right, so whenever you are on the point of the geodesic somewhere here, you are close to a point of the other two geodesics.
And then the remote
Yeah, so if you take any point, for example, V on the line on one geodesic,
yeah,
then there is a point lying on the other two, for example, this one, which is very close.
so that's one.
Less than 11. So the triangles are very thin. So it's called like
Yeah.
delta thickness of the triangle. So this is something
Like, yes. Like a picture, like a space.
yeah, exactly. Yeah, so some examples. That I will answer. So the first example, real things. Simple trees. So one dimensional simple complexes, which with some metric. So so I call it the real tree. So equivalent definition of a real tree is a geodesic metric space, exactly, which is zero hyperbolic. Meaning that if you whenever you take 3 different points, the triangle looks like this triangle. So zero hyperbolic is precisely the RPs. Another example. So hyperbolic defined was we write hyperbolic and dimensional hyperbolic space. So this is something that I have to understand myself as well, but I mean, by definition, this is a four-dimensional and this is the unique simply connected and dimensional complete Riemann manifold of section curvature -1.
Real tree graph? What do you mean real tree? You consider
Real tree, you can, as a definition, you can take a geodesic matrix space which is zero hyperbolic. So really, something which is like
so something like a graph.
like a
With a
like a
with a
is there a sponge? No, it's Let's look at the example, which is like the original complex space, and which was the motivation for this general metric definition. These are these simply connected manifolds with constant curvature -1. So if you generate the distance coming from the Riemannian distance, they are exactly hyperbolic in this sense. Then a trivial example.
So this concept is invented by Gromov or somebody.
I think this definition, I think it was first properly defined by Gromov somewhere, but Gromov attributes it to someone else. This is called like a definition of hyperbolicity. Then there's also something which is called Gromov's hyperbolic metric space, where we don't need that explicit capacity. It works for general metric spaces. It's a slightly more complicated, so I don't define it here, but actually let's come out that every Gromov hyperbolic metric space is quasi-isometric, whatever it means, like roughly isometric to a geodesic metric space, which is hyperbolic. So if we restrict just to geodesic hyperbolic metric spaces, we don't use any examples in this. Then trivial example would be bounded metric space. Bounded metric spaces. Right, so every bounded metric space is considered is delta hyperbolic for delta beginner. The delta is at least the diameter of the diameter space. So this is why this is the non-interesting examples. So for us, the interesting examples are those which are unbounded. And now some non-example. So the typical non-example would be the Euclidean space of dimension these two. So R and this. Then you can immediately see that it's not hyperbolic because the triangle space is look like this, and whatever the other is, you can find it.
Because a linear space limitates of hyperbolic space. So because it's a limitates of the non-Mann hyperbolic space. So what kind of any inequality in limitates it continues is a remain.
Yeah, here I'm just simply saying that whatever the line is, you can take it and why we try not to find this data things. Okay, so now from now on, I want to restrict to like a simple class of complex spaces, just graphs. This will be mostly for the reasons that we'll be working with groups which can be able to as graphs, and also because of boundary of complex space, which I want to define this somewhat easier for just for graphs. So from now on, we work just with graphs. Let's think.
Sorry, I just follow you.
Yeah, so everyone will graph the matrix files. So a connected graph is always a matrix space. But this is a matrix space. The graph is there are two ways how to build graphs as matrix spaces, right? Either you can build graph as again one-dimensional simple complex. So where you parameterize it in the way that each edge has like one. This one way, and one-dimensional space. What I will do is that I will each graph as a discrete matrix space. So for me, the set of vertices is just the set of vertices of the graph. And where I just the distance between 2 points is so shortest path between them. So the graphs become shortest. Yeah, so after I explained I said that we want to target geodesic spaces, but here I'm saying that we are working with discrete spaces. So just learn by this. We just consider something called discrete geodesics. So discrete geodesics and discrete geodesics. It's just now going from some interval, but just intersection with the natural numbers. So from this interval to problem. So in this time, they can view every graph, the graph as a discrete geometric space. So we can get the definition of hyperbolis in the same.
So that in the acyclic conditions, that is complete graph can make a cycle.
It can have cycles, yeah.
And the thing is still hyperbolic.
Well, not every graph, but some graphs are hyperbolic, which are some acyclic graphs are. So some cycles, some graphs and cycles are hyperbolic. Yeah. So I will present them when I get to. Yeah, so I introduce this point of view because I want to define boundary, which is slightly easier in the graph case. So something. And so what's the idea of boundaries? So the idea is that you sit in somewhere inside the metric space. So this boundary is sometimes also a visual boundary. So you sit somewhere in the metric space and you look at different directions, like to the horizon, and the points of the boundary correspond to these points on the horizontal view. So we define so now we have some graph. And we fix some basic algebra, so some vertex. And now we consider the space of all arrays stemming from this fixed point. So this is the set of geometric arrays. So let's say isometric embedding from the integers to v, which span from this fixed point. So meaning that let's say it's natural to 0. So the image of the first point is this fixed point. So as I said, it is fixed, and we want to make it, we want to topologize it. So there's the topology of conversable vectors. The topology. Now it's about so that means one more condition that this graph is locally finite. So what does it mean locally finite? Means that each vertex is incident just to finitely many edges. So under this condition, the space of arrays is compact and present. Yeah, so the metric, I can define metric. So if you take two arrays, rho and rho prime, you can define metric. Actually, the ultra metric in the following way. So the distance between them is defined as the one over the minimum of those and row and it's not the prime. This is an automatic, which is compatible with the forwards. And then some part, and this is why this assumption of local finiteness, and this is again easy to check because if you so the point is memorizable, so you can check compartment just by showing that if you take a sequence of arrays, then subsequent arrays will be convergence, and this is easy because all of them we have a sequence, we have a canonical system from this place for V. We know that the arbiter is over finite, so there are just finite many edges coming out of the function V. So these infinitely many of them must follow the same function. In this vertex again it has the finite many edges, so again infinitely many of the remaining ones will pass to one of the edges and we continue so on to the so it's one. Okay, but this is so this is one space, but this is not yet the boundary. So this space is always zero dimensional. So we need to take some quotient of this space. So we are going to define some selection of this space. So we define an equivalent relation. Those two rays prime are equivalent if there exists some constant, okay, such that these two rays stay close to each other. So therefore every the distance rho prime is bounded by the scale. So again, visually, the equivalence. What is the meaning of equivalence? So we have different rays, but some rays like basically point to the same direction. So they stay close to each other, and then you go to find them. And what is the so now definition? The Gromov boundary. So there are some things to check. So some basic parts, by some standard parts from genealogy. If you have a compact space and you define some closed equivalence relation on it, then the quotient will be again compact and constant.
So what is the Gromov boundary of interest by is that so if the non-one hyperbolic space and Gromov boundary has something is if you consider bounded domain of hyperbolic space, it has a boundary in the if just based on a small bond, yeah, of the hyperbolic space. Then is the boundary is in sphere, right?
The boundary of the standard hyperbolic space is a sphere.
But the Gromov boundary also sphere.
Just for this,
And
for other examples, it can be something else.
yeah.
Actually, every compact space is the boundary of some geodesic hyperbolic space. Yeah, but so here I said that we take a space of rays, what this translation, but we need to check something. This translation goes like the quotation is also. And this is something which again, which in general is not the case. So I will just draw some pictures again. So for example, if you are like you can take one which will describe it, which will be this vertical line. Then you take another one which goes first a bit to the right and then goes again vertically. So this is by definition a historical one. Then you can take another one which goes 2 steps to the right and then it goes up and the same, right? So these rays are all the one to this one. But the limit of these rays will be this horizontal ray, which is no longer the one to this one, meaning that the equivalent selection is not closed in this case. But the point is that when the graph is hyperbolic, then the selection is closed. And the main reason for it is that here it is in the definition. I claim that if there exists some k, but then it turns out that when the graph is delta hyperbolic, this k is always fixed and it is 2 delta. So because of this, you cannot have that. You cannot have 2 geometric rays which are equivalent, but this constant k goes to infinity. This constant is always bounded. And for this reason, the translation on hyperbolic metric space is closed, and you can take the function and it will be a compact Gaussian space. Let me give some
Is that not Gromov with around in his book? Metric space of the Riemann manifold as a thing.
I don't know if it's in that book. It is there's a concept. Spaces is called like let's say spaces something like this from 1987, and that's where we found all these things. Okay, so example. So I believe more when I define the groups. But first, just this basic example that you know is locally finite infinite trees. So when we have locally finite infinite trees, so a thin graph which is locally finite and with cycles, then the boundary is so this is the base point. The boundary is the set of all rays. No 2 rays are equivalent, so actually the boundary is exactly the space of the rays, and it is zero-dimensional space. So in particular, if every branch is in this graph, if every ray in this graph of branches, then the boundary has exactly the vector space. Okay. And now let me move on to groups and functions of hyperbolic graphs. Some problems. With a hyperbolic graph. And G is a group which acts on this graph by axioms or divided by graph optimization. Group acting by then this action is by polymorphism. So I will explain it again just by picture. So let's take some point x from boundary. let's take some point G from the group, and we want to see what is the image of this slide versus how G acts this for this X. So this X is a bidirectional sum of equivalence class of rays. So this X is equivalence class of some rays. So let's say some representative row. So this row is some infinite ray. Now G acts on the graph by asymmetry. So G maps this geodesic ray to another geodesic ray. So G maps this to something like this. So this is row, and this is G applied to. So this is again something geodesic ray. The only problem is that now this ray may not stem from the same base point. G may move the base point. But so what we can do, because it's a geodesic space, right? So we can connect this fixed base point B. We can connect it with this base point of this ray. Now we can happen that the concatenation of this geodesic and this geodesic ray is a geodesic ray, then you have a pin, but usually it is not. When you put them together, it a bit more instructive for me. So, so this is going to be geodesic ray, but what we can do, we just take another point line from the geodesic ray, and we again connect the base point with this. This is probably even not geodesic, but we can continue differently. And we have these geodesics, and they will converge. So these geodesics, they will converge to some geodesic array. And what we do, we take an equivalence class of this geodesic array, and this is how we define. So this is, let's call this one prime, and then G of X will be defined as the equivalence of this prime. I mean, of course, we made a lot of choices on the way, right? So the first choice was that I chose some representative from this class. And then after I chose representative, I was taking some geodesics here. But even these geodesics are not unique, right? The matrix space is in principle, it's not in geodesics, so there can be many different geodesic points. So I was making a lot of partnerships here. Even here, well, okay. Actually, these final geodesics, they don't have to converge, but there is some subsequence which will converge. So another choice was some subsequence. So we made a lot of like arbitrary choices on the way. So this row prime is not defined uniquely, but the equivalence class of this row prime is defined uniquely. So whatever choices we made on the way, the equivalence class of this is always the same. So this is one line. Yes, so now I can proceed finally to hyperbolic groups. And also another thing to check is that there is something in hyperbolic groups. This is again quite straightforward. Yes, so the first thing is to do spaces or two graphs. So there's a standard way how to do it. That is for finite generated groups. So definition of a table graph. For a group, generated by a finite provides data means that X is equal to the inverses from X. So then we can define, so uh, the set of vertices will be the elements of the group, and the edges are the following. So we start as G and G prime as well. D arbitrary and S is homogeneity. So because this is finite, this graph is locally finite, and we can define a metric on the group as a graph metric in this graph. Now the first thing is that again given some choice, right? We chose some generic set. Let's in the part, so S and S prime are two different two finite symmetric generating sets of G. Then the corresponding to graphs are line sheets. Then grade GS and grade G prime are biological elements.
I didn't understand that.
Someone saying something?
No, what is it?
I don't really hear, but I just hear, I just heard the sound, but
Was it someone from?
I couldn't quite catch anything.
Let me check.
I was
No,
trying to
check.
Oh, okay.
Okay, so
Why is it good for us? So you mentioned some parts which I don't know, but part of the graphs or just using the spaces as a method. The two graphs are biology equivalent and one of them is hyperbolic. And the other ones is well, and so the other one. So I is preferred by which is biology algorithms, even by some people who quasi arguments. So because of this, we can just say define G is hyperbolic, finitely generated, finitely generated for example, hyperbolic. If fairly graphic hyperbolic with respect to some finite generating set. Yeah. And there's alternative definition, which I don't see, but which alternative definition is what equivalently the hyperbolic. Or you can only G. So the stabilizer properties are finite. and the action is co-bounded. So for the mean, so that so this is a finite. And the action is co-bounded, meaning that there exists some, let's say, vertex E from the graph and some positive constant K, such that if you take any content graph, there is some point from the orbit of E which is of distance most K. So for there is some G such that the distance between W and times and so let me give again some examples for hyperbolic groups. So the standard one is three groups of finite element generators. And the reason is that the Archaic class with respect to these free generators, they are things, right? Calligraph of each free group of management is a tree, so these are to work. Or you can just generalize this to groups which act on local finite trees with finite stabilizers. This again gives you a problem. Another example, so two-phase groups. Two-phase groups. Sorry?
Surface of, yeah, okay.
Yeah, so I mentioned that negative word for the matrix because, for example, two-dimensional tools.
Sphere.
Or sphere, and yes, sphere has a trivial fundamental and the two-dimensional tools. It works with such. But other surface groups are removed. And you can generalize this thing to fundamental groups. Fundamental groups. Compact multiples. And the reason is that
So you need minus constant one, or you should minus negative section conversion,
yeah, it should be minus. It should be constant and minus.
but it should be constant.
Yes. Because the reason is that so what we need is that we need that the universal cover of such manifold is this hyperbolic space. This is what we need.
Yeah, then actually hyperbolic if the manifold is curvature negative, then you know the covering space is the idea of the hyperbolic. Yeah.
Yes. So this is what we need, and because then the fundamental
Yes, yes.
outside the transformations of this universal cover, and because the Hilda manifold is compact, this action bar the transformations is compact, meaning that yeah, exactly. This means that the quotient is well, the quotient is compact, or we have the universal quotient, which is what we have here. And then basically what I said, the other definition was that acts on a hyperbolic part. So the same is true if G acts on a hyperbolic geometric space, again, there are some conditions, right? So what people most geometrical theory or the reduction is geometry. The reduction is it's bounded, which so and one more example.
And the definition tailoring should be given later.
Yes, so I how much I'm doing like
So it can because it starts like
so
15
minutes.
yeah.
Yeah, so
More than 15 minutes can be okay. So yes, this is the first course of tailoring. The action.
yes, so maybe I'll just okay without too much writing down the mention that this is the idea of Gromov. You can take a random group, random in the sense that you can define groups by in the sense of representation by taking generators and generators. So if you fix the number of generators, it's fixed.
Finally present.
Finally present. So let's say that you fix the number of generators. So you have generators up to GM. Then you want to consider also some relations, and you fix the number of relators. So the number of relations is fixed. It is a longer n. And then also so these relators these are elements of the generators. So these are some words in the alphabet of this. And let's say also fix the length of these relators or the bound of this relation. So let's say that the bound is somewhere. And then you can so you have just by this you just find many groups. So you can count how many of these are hyperbolic. So if you keep fix this n and n and start moving this out to infinity, then the probability bound the group that you get is hyperbolic. So the ratio of hyperbolic to non-hyperbolic as L goes to infinity, the length of the relators, it will go to 1. So in this sense, a random group is hyperbolic. Yeah, okay, so let me now move to the shadowing and yeah, also just one last remark. So the G is hyperbolic, then of course G acts on itself, right? As on its scale gravity. By the and we say that each action of a group on hyperbolic space induces an action on the boundary. So from this action of G on itself or on the scale graph, we get an action by homomorphisms on the boundary. So this is the object that we want to study, this action on the so maybe I will take forward. So now some dynamics, so this shadowing. So let me start with shadowing just in the classical case, then we have space. So we have a dynamic expand now, but X is compact metric and P is a homomorphism. So X is compact metric. Say that this dynamic system has the shadowing property, shadowing. So so for every epsilon there is delta, so then you're going to take a type of points from X, which is indexed by the integers. Then the property that when you move X by D, such this to X plus 1. So this is something which can be close to normal, right? if this was a true orbit, then this distance would be zero, right? And the image of x1 would be exactly x plus 1. So here we are just insisting that the distance is small, so this is something that we both call pseudo-orbit. So for every pseudo-orbit, there exists a real orbit which is close to the pseudo-orbit. So there exists x such that the distance of B and x to equal. So the technical or simple, you can define a notion of pseudo-orbit, which is some approximate orbit, and each approximate orbit is uniformly close to a real orbit. So this is the classical definition, and if you want to define it for marginal groups, then it's the same. So let's just now. And I'm going to on this X by homomorphisms. Let's say that G is finitely generated by some finite set S. And then what this means, so these are the same. Just pseudo-orbit will be some set of points which is indexed by elements of the group. And maybe just bounded the distance between SG and X sub SG is plus a delta for every G and and then we can tell some points which that the distance between Gx and Xg is what I'm saying. So the type proofs what can be I can just say that this the G is hyperbolic. Then this another Cohomology can be solved as a shadow. So I have 6-7 minutes, so let me just put it into the context a bit. So let me present one more dynamic notion, this notion of topological stability. Yes, so here, so again, we have now a few that's what we express. And this actually is for tables. So if you take maybe I don't know, for example, this action by some name or and now you take a different action of the same space, beta, which is very close to this action, very close by this delta, meaning
So the topological stable.
topological stable.
Stable action.
Yes.
What do you mean stable?
This is what I'm going to. So for like another of the same group on the same space, which is very close to the original alpha one in the sense that so of x of distance between alpha s x and beta s x. This was in the for every as through the genetics. So this actually this beta is close to alpha in the sense that the generators very close to the logarithms. So if this is true, then there exists a continuous math from x continuous which intertwines these solutions and is very close together, meaning that if you first start by delta on x and then apply this continuous of phi, it is the same as if you first apply phi and then you apply by this. So this is that this phi intertwines these directions, and moreover, this phi is very close to the identity. So this is where this observer appears. And so we know of course x phi and x is epsilon. So phi moves at every point and very by almost by less than epsilon. So it's very close to the identity. And so this is a notion which generally studied a lot, and even Gromov in his paper from 1987 suggested that this stability should be true for this corresponding action, but he didn't get it to but then it appeared actually the real proof appeared very recently in a series of key papers 2 years ago. And how it is connected with this, so the connection is the following.
No, you proved the Gromov connection. Okay.
No, so Gromov suggested that it should be true that this action is topologically stable.
If shadowing, the topological stable.
No, Gromov didn't talk about shadowing.
Is the terminology?
No, it's not like topology. It's I don't have time to give examples of people studied it.
Okay,
I'm going to finish in 2 minutes, but it's not my notion. It's something that has been studied. Although mostly for like just simple mechanisms, but there are now a lot of examples for marginal groups. But Gromov considered just this notion of topological stability for this action of probability, and he said that it could be true, and he gave some hints. And finally, 2 weeks ago, or 2 or 3 years ago, in a series of 3 papers, some group of people proved it. And the connection is between this, and my result is just that there is this part of theorem is quite simple. Even I don't have to prove it, but I will prove it in just a few minutes. Fact. If we have an atom of G on compartmentalized space by homomorphisms, so yeah, so I don't write it, and this action is the action has shadowing. So I will just say what it means. So what's actually expansive? When we take 2 different points, so there exists some uniform constant, say k. So whenever you take 2 points with y, 2 different points, then you can find some group element G, which moves them k apart. So the distance between dx and dy is bigger than k. So this is So it is expansibility. So when you have shadowing and expansibility, then you make a partial study. Then you have units.
Yeah, Rima, observation.
This is a ring also normal. So shadowing and expansibility. And the expansiveness of this action of the system was known since Gromov already. So this is clear. So just the connection is that this shadowing is some generalization to partial stability implies partial stability. And of this part is part is there. And if I have more time, I will explain it in 3 or 4 minutes. So now.
And so, what is your Mediterranean or
This
River?
one.
I see. Yeah. So, I think we have you have some question. So, what is the motivation of Gromov and the EU to study such of the kind of the action? I mean, that I'm Riemann geometry, so I understand hyperbolic by very interesting. So maybe you just try to see what the analog, but except the graph, is there something wrong?
Except what?
A graph.
Yeah, well there are.
Example.
You mean examples of hyperbolic expressions?
Yeah, that kind of action. So if you have to consider only hyperbolic group.
Yeah, so I mean, so as I told you, for every compartment express, compartment resonance planning, you can construct a geodesic hyperbolic geodesic matrix space whose boundary is
And so yes, that's a fundamental group of hyperbolic space, right? What is a hyperbolic group?
hyperbolic group is a group whose scalar graph is hyperbolic space.
Yeah. But also metric, but not Riemann metric.
No.
Right?
Yeah.
So that except the classical hyperbolic group of the Riemannian space, is there other interesting hyperbolic group?
Yeah, so okay, so these 3 groups, then also these hyperbolic groups are closed under like
Space, yeah. And this is the row space is also
Yeah,
adoption of nature.
yeah, some but there are some groups which act on these zero spaces, and some of them are hyperbolic, but not all of them. Then also this class of groups is called functional operations like free product. So you take a free product of 2 hyperbolic groups, it is hyperbolic. Then also there is random construction, right? You just want to buy if you choose a
No, so that means in the earth answer because that means that usually you say about random only in conjunction is the probability.
Yeah, so it is a probability, right? If you when you have a fixed number of generators and fixed number of generators, then if you choose some group by random with this number of generators and generators, the group will
Yeah, okay, so that you have a lot so that also for Alexander space, that means also hyperbolic group is fundamental group of the hyperbolic Alexander metric space.
Now, I mean, here we have to take a fundamental groups of compartments, right? Because
so I say this outside the degree of the manifold, we have the Alexander space of the negative curvature, right?
about
So that's
so you
I asked you also say the fundamental group also hyperbolic group, right?
yeah, but understand the point here that is B2 is fundamental groups of compartments, right? Because then the action on the universal coverage is
Compact, so that means that it takes a higher. So it doesn't have any theorem about the Alexander space and the group action and the Gaussian is compact. There nothing like that.
it's possible. Just
So if you are not okay on that direction, okay. So If there are no more questions, let us find the speaker again.